Okay, this video is for AP Calculus BC, and this is going to be a little bit more a discussion about how limits connect to asymptotes. We mentioned this briefly in the last video, but we'll go into more detail here. So first of all, we can define something called an infinite limit. And an infinite limit is a limit that, when evaluated, increases without bound to infinity or negative infinity. Technically, these limits do not exist because they're not numbers, and when we originally defined a limit, we said that the y would have to approach a specific finite number. However, most of the time, AP wants us to indicate that the limit is equal to either infinity or negative infinity if that behavior is true for that limit as stated. And there's three general situations where we see infinite limits. One of them would be whenever we have a polynomial, because specifically if we're taking the limit as x approaches infinity or x approaches negative infinity, which we call the right-hand behavior or the left-hand behavior sometimes, polynomials always go off to be positive or negative. So one side goes to infinity, the other side goes to negative. X squared polynomial, both sides go off to positive infinity or both sides go off to negative infinity. So cubics behave this way, things like that. So polynomials always eventually go to an infinity. One side or the other will go to positive infinity. So we get infinite limits. In other words, the y goes off to infinity or the y goes to negative infinity. We call that an infinite limit. So when the limit in itself is infinity, it's called an infinite limit. Okay, the other situations that we have that is if we have a rational function, so we have something in the form of a ratio like this down here. If we have an uncanceled zero in the denominator, so a zero where we're taking a limit as x approaches a specific value, and that value is making the denominator zero, and there's no way to remove that algebraically from factoring and canceling that uncanceled zero in the denominator that can't be canceled, that will be a location where the curve has a vertical asymptote. And that means on either side, the function is either going to a negative infinity or positive infinity. And they can both go to positive or both go to negative, or one or the other could be positive or negative. But when we also get infinite limits whenever we're approaching the position in x when we're about to divide by zero. And then the last case is if you have a rational function that does not have a zero that's canceled, and we're back to the situation where x goes to infinity or negative infinity. It depends upon the degree of the denominator versus the numerator, or just in general. If the numerator is going off to infinity faster than the denominator, then that means there's a tug of war between the two, right? The denominator going to zero wants to force the y to go to zero. The numerator going to infinity wants to force it to go to infinity. And if the numerator is larger, it's going to win out and make the whole thing go off to an infinity. So those are three situations where you'll get infinity as a limit, as the y value. Okay, limits at infinity are limits when x is approaching infinity or negative infinity. So let's say that, for example, you want to take the limit as x approaches infinity, but you have a rule which is e to the negative x. That's an exponential decay curve. So the limit as x approaches positive infinity means that the y is approaching zero, right? So if that's true, if this limit at infinity is not approaching an infinity, it's approaching a number like zero, for example, then we say that the function curve has a horizontal asymptote of the horizontal line y equals that number. It could be zero or it could be another number. On the other hand, if you have, let's say, the function e to the x, the limit as x approaches infinity of e to the x goes off to infinity. So a limit at infinity can produce an infinite limit, or a limit at infinity can produce a number. For the exponential decay course here, or case here, a limit as x approaches negative infinity goes to an infinite limit of infinity, right? Whereas regular exponential growth, as limit as x approaches negative infinity, actually goes to zero over this side. So for exponential growth, we have a horizontal asymptote only on the left side and an infinite limit on the right side. And for exponential decay type curves, e to a negative power, we have a horizontal asymptote on the right side and an infinite limit on the left side. Okay. So Can you evaluate limits without graphing? Sometimes you can if you understand the behavior of the underlying function. So let's say, for example, we have limit as x approaches positive infinity of x to the fifth over e to the x. In this case, both the numerator and the denominator are both going to infinity. So this is like an infinity over infinity, which is what's called an indeterminate form, because we could have something like this. Let's say we had the limit as x approaches infinity of 3x to the fifth over 2x to the fifth. Well, these are both going off to infinity, so that's like an infinity over infinity. They're both racing to infinity, but they're both going roughly the same speed as they go off to infinity, right? They're increasing as x to the fifth power, both the top and the bottom. And actually, we know by factoring and canceling that you can factor this out, and that's the limit as x approaches infinity of just 3/2, which is a constant. So that means that this top half is always 1.5 times bigger than the bottom half. And that means that even as this is an infinity over infinity, or like a billion over a billion, this is 1.5 billion over 1 billion, so the limit is 1.5. So in this case, the tug of war, they both kind of evened out, and we ended up approaching a constant. This is how we would get a horizontal asymptote if the line y equals 3/2 on the right side. Okay, with this one, where we have x to the fifth over e to the x, which one actually goes to infinity faster? In this case, the exponential e to x goes to infinity faster than x to a constant power. So that means the denominator is going to win out, and this limit actually goes to 0. Right? On the other hand, if this was the other way around, if this was the limit as x approaches infinity of e to the x over x to the fifth, then you'd have a bigger infinity on the top and a smaller infinity on the bottom, and this limit would go off to infinity. Okay. Another case where you have sometimes indeterminate forms would be something like this. Let's say you have two numbers which are both multiplied together. So we have a part of the rule that's x squared and a part of the rule which is x minus 1. Let's say we're taking the limit as x approaches negative infinity. Well, if we square that, this is becoming a large positive number. And this is a large negative number, and we're subtracting 1 from it, which is a large negative number. So we're multiplying two giant numbers together, one's positive and one's negative. So I can definitely state that this limit as x approaches negative infinity of that structure is going off to negative infinity. So although we're not really allowed to do, you shouldn't really write things like this, because some of the grading rubrics for AP say penalize the student if they do arithmetic with infinities. You can think about it and get an idea of what's happening in the function curve from the behavior of the functions. Okay, there is actually some formal procedures for how to do things too, but we learned how to deal with things related to horizontal asymptotes, where we're taking the limit as x approaches infinity or negative infinity back in Honors Algebra 2. If we're taking the limit, say, as x approaches negative infinity, x to the fifth plus x to the fourth minus 2x cubed over 3x to the fourth minus x cubed, the larger degree is in the numerator. That means the numerator is definitely going to infinity faster, and that means this is going to approach an infinity, right? In fact, this is going to go off to negative infinity on the left, and if you go to the infinity on the right, this will be a positive infinity on the right. If the degree in the numerator is smaller than the degree in the denominator, that means the denominator is winning out, and this will approach as 0, both on the left and the right-hand side, so we have horizontal asymptotes of y equals 0. And if the degrees are the same, x to the fifth, then that means that eventually, you can think of it this way, this is always 10 times bigger than the rest of this stuff, and this is always 10 times bigger than the rest of the stuff, which means you can approximately cancel that. This limit is approximately the same as just the limit of 2/3, and in fact, you can show that this is exactly equal to 2/3. There's a procedure which I'll show on the next screen about how to do that more formally, but you can think about that. Actually, AP doesn't require that we do a lot of things. If you were presented this problem and you wanted to evaluate the limit, you could just note that these degrees are the same and just go straight to the answer as 2/3 without any additional work. Right, so you should familiarize yourself with those concepts so you feel comfortable dealing with polynomials over polynomials. Now, there is a procedure where you can formally evaluate this. This is the formal procedure, although we don't, even AP doesn't require that we use this. You can take you can take the highest power in the denominator, in this case x to the fifth, and divide every individual term by that same x to the fifth, which means this 2x to the fifth becomes 2x to the fifth over x to the fifth, x to the fourth over x to the fifth, and so on. And then if you take the limit as x approaches infinity, anytime the degrees are the same, that will turn into this constant 2, right? But this, 4 of these x's cancel one of these x's, so that's equivalent to 1 over x. 3 of these x's cancel 3 of these x's, leaving 2 over x squared on the bottom. And anytime you have a limit as x is approaching infinity of a constant over a variable, those things all go to 0, leaving just the coefficients 2 over 3. So that's why this is always just the leading two coefficients, 2 over 3, if the degrees are the same. But this is the formal procedure to show why that's true. You're not ever really required to do this, though. Okay, so in practice, if you were given this limit as r approaches infinity, I would just note that there's a lower degree denominator on the top, or in the numerator, than there is in the denominator on the bottom, so this is simply equal to 0. If you wanted to say the limit as x approaches negative infinity and the higher degree is in the top than the bottom, and this is going off to an infinity, you can just immediately say it does not exist. Or if you want to be more precise, you can say, well, if I had a negative infinity cubed, this would be a negative on the top, and a negative infinity squared would be a positive on the bottom. So that's going to swamp out the rest of the terms, and you could state that this is negative infinity if you wanted. And then here, I'm thinking if you multiply this out, this is 6t squared plus 5t, but on the bottom, if I multiply this out, I get 2t minus 2t squared, and then minus 3 plus 3t, which means if I rearrange this, it's negative 2t squared plus some stuff, and on the top it's 6t squared plus some stuff, which means the degree on the top and bottom are the same. So this limit is going to be equal to the ratio of the leading coefficients, which is 6 over negative 2 or negative 3. And that's all you have to do. If you wanted to be really formal, you could do the whole procedure. I'll do that on this one, which would be to say that this limit as x approaches negative infinity of divide everything by x squared. So that's 3x cubed over x squared minus x over x squared over x squared over x squared plus 2x over x squared plus 1 over x squared. And then that simplifies to, let's see, 3x minus 1 over x. And then this is going to be 1 plus 2 over x plus 1 over x squared. All of these ones which have constants over something going to infinity go away, and this is 3x over 1. So if you're taking the limit as x approaches negative infinity of 3x over 1, that's just replacing the x with a negative infinity, which is going off to a negative infinity. That's a whole lot more work than just noting, hey, this is larger than this, therefore it's going to an infinity. And this is what they would expect. They wouldn't expect you to do this. Okay, what about this one? The limit as x approaches infinity of e to the negative x squared. We see this one a lot, and actually we see this a lot in Calc 3 the next year as well. So how can you think about that? Well, there's a couple ways to think about it. One is to think of this as, this is like e to the negative something, which is an exponential decay curve, and that something is infinity being squared, so it's like an infinity, right? So if you're imagining you're going off to infinity, this is simply going to 0. So this limit is just 0. And you can just assert that that's true. You don't have to draw anything. In fact, you probably shouldn't actually show this, because you shouldn't do arithmetic with infinities, but I like to just think it through. Another way to think of this is that this limit is equivalent to the limit as x approaches infinity of, if you think of this as being a fraction, this over this, you can move this to the other side of the fraction and make it positive. And then you have 1 over something which is e to infinity, which is infinity. And any constant over a giant number is going to 0. All right. Let's see. What else do we have here? Oh, this is the last example. Okay. Find the horizontal and vertical asymptotes and then check by graphing. Okay. So analytically, let's look at vertical asymptotes. Actually, let's look at horizontal asymptotes first. Horizontal asymptotes happen. Well, we'll check those by taking the limit as x approaches infinity. So if I do this, I'm noting we have the same degree on top and bottom of x squared, so 1 over 1, this limit is 1. And the limit as x approaches negative infinity would also be 1. So that means that there is a horizontal asymptote of y equals 1, and it's present on both sides. So to find horizontal asymptotes, we just take the limit as x approaches infinity and the limit as x approaches negative. Okay, for the vertical asymptotes, we're looking for uncanceled zeros in the denominator. So maybe I could rearrange this a little bit. X squared minus 1 is the same as x minus 1 times x plus 1. You can't factor this, so there's no way to cancel either of those. And that automatically means that the equation x equals 1 and x equals negative 1 are the two vertical asymptotes. Okay? Now this just said define that, so we're going to stop right there, but I think we'll go ahead and throw this into a calculator to graph it just to see whether or not we got this correct. If I go here and clear out these graphs and put parentheses x squared plus 4 divided by x squared minus 1, and graph that, let's just do zoom 6 to start. Sure enough, there is a vertical asymptote at negative 1 and 1, and on the right side and the left side, it seems to be approaching the line y equals 1. So perfect. Back there. Right, and that concludes that. We can use limits and see their connections to the asymptote.